Yeah, thank you, Dr. Moya. Thank you, Fernando, for this very nice introduction. I'm happy to be back here. I think it's about 2.5 or 3 years ago that I was presenting to you about the same subject, but the subject was in a different state. I think at the end it might, we think we are ready to change clinical practice on the data that we have, at least for ourselves. I would like to lead you through that journey. It presents a little bit research of 6-7 years with about, I don't know, 20 undergrads and 3 or 4 master's students involved. You will see that at the end. So this is, can you see? I'm not transparent, right? So unfortunately, can put myself where I want. It doesn't work. So. You're good. Okay, so yeah, so this is McMaster, and this is Nürnberg Medical School. So I just show you this is. I did my studies here and had my pediatric training here. Then went to Bern and Zurich. Was there about 8 years, and had a chair and chief position here in Greifswald for about 10 years, and then got attracted because started to do the same thing here all the time. Got attracted by this research chair in Hamilton. Big unit, about 250 babies below 1,500 grams, and a catchment area of 27,000 births for this all region here up to Niagara Falls here. This is basically close to Toronto. And then decided to go back to Germany to help with this building up this Nürnberg Paracelsus Medical University, which is a private university, which is a new model in Germany and incorporates elements from Canadian, from Mayo Clinic, and basically is a little bit running against the federal state funded universities, and I like that if there's a little bit of competition. So yeah, so Nürnberg is here, here's Berlin, here's Munich, here's Cologne, here's Hamburg, all nice, beautiful cities. Nürnberg has about 550,000 people living here. The catchment area is about 1.2 million. And there are few hospitals and one true university, which is Erlangen, which is good in medical, technical stuff. This is Nürnberg, a nice city. Was relatively much destroyed in World War II, got rebuilt, and you still see this nice castle here. There are, because we have a nutritional lecture, so you have the Nürnberg sausages here with or without bread, or with and without sauerkraut. But imagine I eat sauerkraut maybe once every 3 years, so it's not that all Germans eat sauerkraut every day. It's not. There's good krautrock, but that was in the 70s and 80s. That's different. And there's some gingerbread, which also was very much invented here. And this is the archetype of Christmas market in Nürnberg, which is really, truly beautiful. You can really immerse there. Lots of public drinking and lots of public fun there. I must say. So, but now, once more, thank you very much for this invitation. I really enjoyed it. I spent a good time today with Carl already out on the beach. Got a lot of fresh breeze, and I wanted to incorporate a few pictures into this presentation, but unfortunately I couldn't transfer the pictures from my cell phone to this one. But so now coming to the core of my presentation, and I will distract you now for about 45 minutes. I hope that works. I have to do a disclosure first. I discuss the off-label use of infrared analyzers, and there are basically two, the SpectraStar and the Myris human milk analyzer, and I have no relevant financial relationship of commercial interest in regard to this presentation. I have and had advisory roles and speakers with Nestle, Milupa, Mead Johnson, Abbott, Humana, Baxter, Fresenius, Icaria, Medela, Prolacta, Hamilton Medical, where I met Carl again, and I received an unrestricted research grant from Prolacta, but we are not talking about this product at all. So I think I'm equally biased in all directions here. So the objective of my talk here is to review the underlying principles of growth and nutrition, and know that you are very much in growth and nutrition, and maybe I'm carrying owls to Athens, how you say, but still I need it for the development of the principle, and I would like to compare current concepts, benefits, and limitations of breast milk fortification. And this talk focuses mainly on preterm babies, mostly on ELBW babies. These are all my email addresses in case that someone wants to have this presentation. So there are special rules for the Game of Growth. Nutritional intake of preterm infants is fully under control of neonatal staff. And that is different from term babies. Term babies can regulate what they drink, and they drink sometimes more or less depending on the quality of breast milk that they are experiencing. But preterm babies can't. They are usually gavage fed or on total parenteral nutrition. There's ex utero no clearance via the placenta, and the renal capacity is limited. So very low birth weight infants have to metabolize what we are filling into this system, VLBW infant. There's no option for self-regulation, and there's no way to escape. So these babies have to deal with what we do with them. So the aim for postnatal growth is very simple. The American Academy of Pediatrics, and I like these American statements because they are one sentence and it encompasses all, recommends that preterm infants achieve rates of growth and composition of weight gain for a normal fetus of the same postmenstrual age and to maintain normal concentrations of blood and tissue nutrients. Isn't that fine? One sentence, but very hard to do at the end. So let me lead you through this slide. Here we have the gestational age, here we have the weight, here we have intrauterine percentiles. That's the best what we have just right now, be it Fenton curves, be it intergrowth data or whatever. They all are cross-sectional data of babies that have been born at known gestational ages, and then we just plot the distribution. This is the 50th percentiles and the 97th and the 3rd percentile. And baby being born here around 24, 25 weeks, at the end when the baby is discharged, has changed his birth weight by a factor of 6. So it means 1/5 of the body mass that the baby has here at discharge has been accomplished during the stay in the NICU. So it's a huge responsibility of us to make the baby grow here somewhere, somehow, according to these percentiles. And that will be the subject of my talk for tomorrow. What is the approximate best trajectory for a baby that is being born preterm? So we need to make it the transition here somehow. So it's about weight gain. But it's not only about weight gain, it's also about organ differentiation. So everything in the baby is immature and needs to grow and also needs to differentiate. And you see here for the brain, this is a 20-week-old brain, an MR scan, and this is a baby with 42 weeks. You see the brain has about doubled in size in one dimension, and because in most humans the brain is a 3-dimensional organ, it comes up to a factor of 6 to 8 at the end. And yeah, it's true. And you see that the structure changes as well. This is basically close to a lissencephalic brain. There is no gyration, nothing. And here you see how the gyration and also myelination has happened and has improved the surface of the brain, which is needed to increase the terabytes that we can store here. So this transition also needs to happen. So it's about organ differentiation, and the most critical one at the end for long-term functionality is the brain. And you can influence it. You know, this very famous study, very frequently quoted by Stevens, who looked into nutrient intake during the first week and showed that the MDI, so the mental developmental index, goes up by 0.46 points by each kilocalorie that you get into the baby during the first week of life, and by 8.2 points for each gram of protein that you can feed the baby more with. So there is a clear relation between nutrition and brain function. There are other data about brain growth and later outcome, like this study that goes far beyond the neonatal period up to the adult period. What they depict here are babies that had a small brain at birth, had a normal brain at birth, and those with a small brain at birth that had a catch-up growth. And these are the IQs at the age of 2 years, 6 years, and as adults. And you see that these babies that had a normal head growth and normal trajectory, they have an IQ here of about 110 plus minus some standard deviation. And those where the brain was, where they started with a small brain and the brain remained small, is about 10 points below. And those where they started with a small brain and then had catch-up growth with the brain, they had nearly a normal IQ. So brain growth at the end, brain size matters. In this study, it was very nice because they controlled for parental head circumference as well. And There are other data, I like this one very much, where you look into correlations. So these are only Pearson correlations, only correlation coefficients for later outcome at different ages here, for neurodevelopmental and cognitive outcome, and how does head circumference, height, and weight correlate with these parameters. And you see here, it is head circumference that correlates with cognitive outcome. It's not weight, it's not height so much, but it's head circumference. Again, brain growth matters, and we need to do the best for the baby's brain, and we have only a limited period of time to do that right. But things are a little bit more complicated, and again, I need this physiology to help to understand why target fortification might make sense or will make sense. So we went already through this part. Now I would like to draw your attention to these two little insets here. This is about body composition. Now you see here, again, gestational age, 22 weeks up to 40 weeks, data from two different authors, Michael Kramer from Canada and Eckhard Ziegler from Iowa City. And you see here that the body compartments grow with different speed, with different velocity. So the blue one here is protein, and the one below is water. So that is the lean mass. That is what everybody of the adults above 30 would like to have as much as possible, lean mass, and ideally not too much of the green, the fat mass. I'm fighting the same thing. But yeah, especially since I moved to Nürnberg, you know, with the sausages. But you see that the lean mass here is maybe, it's more a linear growth here, and you see it here with a different approach. This is from 76, this is from 2001. Both show the same. The protein mass is more or less growing in a more linear way, whereas the fat mass starts to accumulate at the age of 30 weeks here. 30 weeks, both show the same thing, and then goes over proportionally up, which means babies at the end, once they are beyond 32 weeks, need to accumulate a little bit of fat mass. That is necessary because fat has a metabolic meaning and a metabolic function. It secretes leptin, which is a very important hormone, and does a lot of other stuff. So we need to make the babies grow the right way. So it's not only about gaining weight, but it's also about gaining the right proportion here. Enough fat, but not too much fat. And that means that nutrition might need to change from here to here. And it's not only about growth rates. So this is something where I would like to tease you with a little bit, and I will give you the answer more tomorrow. But all of the babies lose weight after birth here, and then they restart to grow. In all honesty, they continue to grow, but they are losing water here, so that we experience a shift. And now the question is, where does this baby need to grow, on which of these percentiles? All these percentiles here, all these growth trajectories here have more or less the same growth velocity, so or weight gain in gram per kilogram per day, because it is the same slope. So you have the same delta, and paradoxically, the growth rates here in these babies, the weight gain that grow here, are even higher compared to those, because the denominator is smaller at the end. So in gram per kilogram per day, these babies grow faster compared to these ones. So currently, where these babies need to grow is unknown. Why does it matter? It matters because depending on where the babies are here, we don't only have a difference in weight, but we have also difference in weight, in body composition. So you see here that the lean mass is not changing so much, but the most variable compartment is fat mass here. And the amount of fat mass to lean mass at the end has something to do with later outcome, and I will delineate that a little bit more tomorrow. But what I would like to draw here your attention on is that body composition at the end matters. It's not only about weight, but it's also how the weight is being composed. So I learned if you give a lecture about nutrition and growth in preterm babies, no lecture without that goes better maybe if I'm here. I still see everything. Is to show this Ehrenkranz paper, which is very frequently quoted. So you see here the intrauterine trajectories, or the percentiles, the 10s and the 90s and the 50s percentile. And these are babies from 24, 25, and 26 and 28 weeks. and those are published trajectories how these babies grow. Is that right? Most likely not, because as we heard from the AAP, they should follow somewhere these trajectories in utero. And if we would see such a growth phenomenon in a baby or in a child that is 4 years of age that deviates from the percentiles, today I saw endocrinologists in the outpatient clinic and so on, they would be very much worried, or gastroenterologists, that this baby would have a severe disease or maybe even suffering from child abuse. And you would maybe call CAS in Canada to protect the child, if you see this one. In neonatal medicine, for a long time, we didn't know better because we were very much focused on adaptation and cardiopulmonary adaptation and ventilation and we were facing a lot of problems with sepsis and growth and shortcut and BPD. I think these times are over. You successfully managed to get sepsis rates under control, so you can focus a lot on other phenomena like growth, because you don't always go back to square one when you experience a sepsis. So I think these growth trajectories should be a phenomenon of the past, and I will talk about that a little bit more tomorrow. And these also very recently a paper from a US big center showing such growth curves as their standard. That cannot be right. So is this postnatal growth retardation, is that a problem? It is. You see this study here where 33% of the babies at birth were SGA, and they were all babies, VLBW babies, and at discharge it was 63%. And the question is, how does that happen? Most of these babies were on breast milk. How can that happen that they experience so much growth retardation? Because breast milk is best, things that I think, but we need to be a little bit careful, as Dr. Moya said. So let me review the physiology a little bit. What you have here is depicted is the relationship of protein intake here in gram per kilogram per day and nitrogen retention, which is another measure of lean body mass accretion. So if you retain nitrogen, that means you retain protein, and that means you retain or you build up lean mass. And there is, from all the data that have been published, a very close relationship between protein intake and nitrogen retention. You can calculate growth from nitrogen retention by using this conversion. 200 milligrams equals 10 grams of growth. So 10 grams of growth here, 10 grams per kilogram, 20 grams per kilogram. To achieve 20 grams per kilogram weight gain, you need 3.5 grams per kilogram per day. That's what we use in practice. And that is where these data, that is where these recommendations come from these data. And again, it is a very linear and very close relationship. So the thing, if you feed babies, it's a little bit like changing ventilator settings and then see that the blood gas analysis changes, only the kinetics is a little bit slower. When I change the ventilator, blood gas analysis changes a little bit faster. But if I give the babies more protein or less protein, then growth rates will slow down or increase. So this is very important, and you need about 1 gram per kilogram per day for not to grow. If you give less, then the baby is losing lean mass. So, but it's not only about protein intake. Protein needs to be seen in the relationship of the amount of energy that the baby gets, because there's also energy be stored and energy be needed to build up protein, to build up lean mass. And these are very basic data that have been established in the late 70s and in the 80s. And what you see here is on the x-axis, the metabolizable energy intake here. On the y-axis, the protein gain, which is another measure for building up lean mass. You can multiply this with about 6. And then here, the net protein intake and the characteristics, what happens if you give certain fixed amounts. So let's look at these characteristics. So this baby gets 2 grams per kilogram per day. And if you don't give enough metabolizable energy, that means fat and carbohydrates, then your growth rate will stay below these 1.5 or 1.6. And it will reach the maximum here at around 100 kilocalories per kilogram per day. And then there will be a saturation. Why is that happening? So here, you have enough protein, but you don't give enough energy, so there is protein breakdown, and the protein is not being used for what you intended to do it, namely use it at building blocks and to build up lean mass. Once you increase the metabolizable energy intake, the lean mass build-up increases, and this plateau comes from the fact that now all building blocks, so all protein is now being used, and there's nothing left here. So you can increase the energy more and more, but because you have already put all building blocks into protein and lean mass build-up, you won't achieve more protein gain. The only way to achieve it is by increasing then more protein. So the short sentence from this long explanation is that protein and energy ratio need to be balanced. There's no need to have high protein intake and not enough energy. There's no need to have no protein and a lot of energy. And that's what we do sometimes in clinical practice. The baby's not growing. Oh, let's give him a little bit more protein. Or let's give him a little bit more duocal or whatever, without knowing what is in there. And we recently had a baby that was a 24-weeker, was about 700 gram, doing very well, had one day, had a less invasive surfactant administration, was not even intubated, and started to go into this period after the first 10-14 days on full enteral feeds, but then we realized the baby doesn't grow well. So because we could not measure milk content at that time, we said, okay, let's give him a little bit more protein. So we increased the protein content by 0.5, and 2 days later, the baby looked septic. Edematous, bad. So we started septic workup, was negative. We started antibiotic treatment. The whole thing remained negative. So we said, what did we do? Yeah, we gave more protein. We measured blood urea nitrogen. That tripled within 2 days. So then we said, so let's cut that back, that protein. Maybe we poisoned the baby with protein. And did it. 2 days later, the baby was normal. Blood urea nitrogen went down, the edema disappeared, and so on. I just wanted to draw attention on that. By doing this pragmatic approach, we are sometimes generating unhealthy conditions, potentially. And I will show you that a little bit later during this talk. So this was something that I drew down by hand for the talk in Orlando. And basically what happens here is we have our amino acids here, which have this structure here. So we have 2 amino acids, and you can combine them, and then you start to build up a protein if you do that a few times. So at the end, you generate a little bit of water, and you generate here the protein from building the amino acids together. That is the good pathway, what we would like to have. The bad pathway here is that the protein is not being built in, but is being used to generate energy. So then basically this amino acid here, this NH2 group is cleaved from the carboxy or carbon skeleton here. The carbon skeleton is fed into the gluconeogenesis or wherever to generate energy, and the H2N needs to be eliminated by building up urea here. So, and that is a very costly process, and that also binds a lot of water. So this is the bad pathway, and this is the good pathway. So where do we achieve good growth on these characteristics is here, because here we give enough protein and we have enough energy. So here we achieve good, appropriate growth, optimum accretion of lean mass here. If we give more energy, then we would not only accrete lean mass, but also fat mass, which we might want or might not want. If we are in this range, we will get a proportionate growth. So fat to lean mass is okay here, but we will not get the optimum growth here because we don't put in enough protein. That is depicted here. All this area, we do not achieve appropriate growth because the protein intake is too low. We have inappropriate growth below the genetic potential of the baby. Here, the energy intake is too high. So we get a disproportionate growth. We get excess fat mass and might have problems with triglycerides and with glucose tolerance later here because that is not balanced anymore. And here, the energy intake is too low, but here we give enough protein, but not here. So here the BUN might get up, but we might not build up enough lean mass here. So at the end, if we look into where is the area of optimum growth, then we are here. Sorry. This is the area of excess growth, and this is the area of restricted growth. And you see there are many more conditions leading to restricted growth than to optimum growth. So now physiology becomes a little bit more complicated. So we go away from protein and from energy, but look into the two other components in carbohydrate and fat. And this is a very nice study from Sudha Keshyap from New York. What she did is in 3 groups of well-growing babies, she gave them the same amount of protein, well-growing, very low birth weight babies, 4 grams per kilogram per day enteral protein, and 130 kilograms per kilogram per day of energy. So all got the same. And then she varied in these groups the amount of carbohydrate to fat. So here, 1/3 of the calories, of the non-protein calories, were given by carbohydrates, and 2/3 by fat. Here, it's the other way around, 2/3 by carbohydrates, 1/3 by fat, and here it's 50-50. And the surprising and a little bit unexpected result was that the weight gain here was lower compared to here, and this is about 3 grams per kilogram per day, which is significant. Over a period of 3 to 4 weeks, you end up with 200-300 grams of difference in these babies. And also the head circumference was affected. This doesn't look like a lot, but it's 0.05 here per week. So that adds up at the end. And as I said, brain growth matters. Also, body composition was different. They stored a little bit more fat, but they also stored much more protein here. And why did it happen? So she measured protein oxidation in these kids with different techniques. And you see here it's 1.05, and here it's 0.85. So here's much more protein oxidized, means it is not being used as building blocks. It is being destroyed and used for energy. Maybe because the carbohydrate was too low and there was too much fat, which first goes into the fat cells and is not so easy to mobilize, whereas here there is enough carbohydrates and not so much fat. So here's less protein oxidation. So if we put all that together, then preterm infants have high growth rates and thus high nutritional needs. Protein and energy intake determine growth rates. Carbohydrate to fat ratio modulates growth rate and impacts body composition, which is of relevance if we are talking about DOHAT, developmental origin of health and disease, which is a very up-to-date research area. Okay, so now what is needed to achieve these good growth rates? Here we have the gestational age. Again, here we have the weight. Here we have the weekly weight gain, and here we have the weight gain in gram per kilogram per week. And this is this curve here. And you see that term babies have about something 3 to 8 gram per kilogram per day of growth rate, and preterm infants 12 to 18 or even 20. So if we take our linear relationship, then we can calculate the protein intake that is being needed, and term babies need 1.2 to 5, preterm babies need 3 to 4.5 gram per kilogram per day. Assuming an intake of 100 milliliters per kilogram per day, that fluid that you feed the babies, potentially breast milk or whatever, should contain 1 to 1.3 gram per 100 milliliters of protein for term babies and 2 to 2.9 gram per 100 milliliters in preterm babies. Surprisingly, Mother Nature has exactly figured out that breast milk contains 1 to 1.3 grams, and we are the living example, at least those who have been breastfed. Unfortunately, I was only breastfed for 6 weeks overall. Yeah, it's about brain growth. So Mother Nature made it happen here, which is due to evolution, but it will not work for preterm babies. So if you look here, what the protein content in breast milk is over time, this is in weeks after birth, and from 20 months, then you see here there is a decline or decrease of protein content after birth during the first 4 to 6 weeks. And there's also a huge variation between mothers. And these are the recommendations for preterm babies. So there is no way that breast milk will have enough protein content, maybe in the beginning, a few months, but after a few weeks, that will not work. And so what has been invented and what everybody is doing since 20 years is that we do the routine fortification with commercially available human milk fortifiers, and they are added at a fixed dosage. So we don't vary a lot. We put in one package per 25 milliliters or whatever, because that has been calculated. So what we do with applying this technique is that we're bringing up the protein content, but also the caloric content by a certain fixed amount here, 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 and but we don't get rid of the variation. And you see here for the first week, all preemie babies would be very happy because they get enough protein. Already after week 4, there's 1/3 of the mothers that do not produce enough, where the babies do not get enough protein, despite they are being fortified, because the natural variation is so large. So these babies most likely would not grow. And that is why extrauterine growth restriction at discharge is observed in 58% of VLBW babies fed predominantly standard fortified milk. That is still an issue. And I don't know about your data, but you need to be very, very careful if babies are on fortified breast milk, that they really meet the nutritional aims. So there is one paper from Asanloglu together with Eckhard Siegner that shows what do we do if we have a strategy to fortify differently according to BUN. That's what they did. So he did a randomized control trial here where he applied 6 fortification steps: HMF 2.5, 3.755, 6.72, and then plus additional protein. And it was always topped up when the BUN was low. I think it was below 8 or below 6. And it was scaled down when the BUN was above 14 or 16. Those were arbitrary units that they used, but they had 2 groups here, standard and adjusted fortification. And this is a population, all healthy growing babies. And you see that standard fortification here leads to 14.4 gram, whereas adjusted fortification to 17.5. And that's something that where we would feel comfortable reaching 17, 18 grams per kilogram per day here. 14 is definitely not enough. There are a few babies that reach the 17, but there are also some that only have 8 or 9. But still the same here. There are some that the average grows with 17, but there are maybe 30% of the babies that only grow with 14 or even below. So adjustable fortification helps, but doesn't get rid still of the variation and of this imbalance. These are data from our study where we looked into the variability of breast milk composition. This is just for energy. I show you the other data as well. And these are 10 mothers where we had between 20 and 50 samples, breast milk samples. And you see here that this mother here, where is it? Sorry, this one here, she produces breast milk with 65 kilocalories per 100 milliliters, which would be 20 kilocalories per ounce, I think, which is according to protocol, so to say, what she does here. But this mother here only produces 60 kilocalories. This one is even below 60. This one is variable. This is very high. Yeah? So it's a huge variability in terms of energy content. So we graphed that a little bit more in detail for fat, for protein, for carbohydrates, for these different, for the moms, and you see with the averages, they are all over the place. And I told you about calories, about these macronutrients, but I also told you about protein to calories, so to energy, unstandardized, and about the non-protein calories as carbohydrates here. And you see it's between 40 and 60%. So like the experiment from Sutta Keshap. So these babies would experience different growth rates, though they are would get the same. Jay Kim from the San Diego group did a similar analysis and just published a paper just a few weeks ago and showed the same thing, that for term babies and for preterm babies, the values are all over the place and are not within the recommended ranges, which is between these two bars. So the data or the analysis that was a real eye-opener for us, what happened, are shown in here. You see here from 850 milk samples from 10 mothers of preterm infants, plus from 40 mothers from term and preterm babies, 4 mid and hind milk. 4 mid and hind are the colored ones here, according to these symbols. And these ones here, the gray ones, are the 850 milk samples. And I first thought there are mothers that produce breast milk that is just diluted or concentrated. The thing why I thought it was, then we have an option that we just up-concentrate breast milk by taking some water out. There are different techniques now available. Then we would fix the problem. But unfortunately, when we did this plot, and I think nobody has done that before, and we have published it 2015 in Acta Pediatrica, and you look here for protein to fat. Fat is the major energy component. Protein is the protein component. So there need to be a balanced relationship, and you see there is not. Here are babies that receive about 1 gram and no fat. There are babies that receive about 1 gram of protein, that's fine, and a lot of fat. And there are babies that have a lot of protein here, but no fat. These babies cannot grow, impossible. It doesn't work because this PE ratio, this PE theorem is violated. And you see it here for lactose and protein as well, and for fat and lactose as well. So there is no relationship of the different components. So it's like the menu that you have on your plate. So one of you has more potatoes, the next one has more fish, the next one has a little bit more of whatever, right? So steak, yeah. So term babies don't care because they can regulate it. They feel what they are drinking. That's the same thing. If you eat a cheese fondue or a steak fondue, so a meat fondue, you eat differently. Why? Nobody tells you there's so many calories in. You feel it. And term babies do that. Preterm babies can't. That's why I said in the beginning the Games of Thrones rules are important. And we are violating these. I don't want to be misunderstood. Breast milk is super, it's excellent, but it has its limitations with this gross physiology. So here is protein and fat for 13 mothers where we had more than 21 samples. And you see they are color-coded per mother. And you see this mother produces a milk that is different from this mother or from this mother. And it is on one hand consistently different, but there's also an overlap. So even the same mother here gives you one day more steak and one day less steaks, one day more fat, one day less fat here. So, and what you see here, fat versus protein, is nothing different than what you have here. So I told you the best area of growth is here. So do the same thing. I can show you the best area of growth is somewhere here. And you have areas here where you cannot grow because you violate the assumptions with this breast milk. And you can even go into these different areas and calculate what that would mean here. Because the babies don't get enough protein here, if you would feed them, even with standard fortification, at the end, if you take the Stevens data, they would lose 9 MDI points, and depending on where you are. And on the other hand, if you are on the excess, then you can say, okay, these babies will get so and so much body fat too much, so and so much weight, or here the BUN would go up, and so on. So, and this, in reality, that's something that we experience. So just to add more of an unbalanced diet, I would say, will not help to fix the problem, right, of some babies not growing well. These are data again from Jay Kim's group here, who it was published here 2017, just right now, and he showed the amount of samples that are above and below 10% of the expected values, and it's considerable. So basically, it confirms what we have published there as well in a different way. So why is that also important? It is also important for babies on donor milk. Donor milk is usually generated here from moms that are lactating already for a while, and we know it all works well. Usually you don't get donor milk from moms here, it's here. And the protein content of donor milk is on the lower end. These are data from Tennis Fenton. And in our study, and I will show you the data later, is that all moms with donor milk were in the lower range of protein, and the donor milk samples are the black ones here. So babies on donor milk might have an additional problem of not growing well because the breast milk is not rich enough in protein. And there is this paper from Deborah O'Connor, which was published in JAMA. I was a co-investigator there, so it's my first JAMA paper, maybe my last one. Never know, if you get one, it's fine. But I was only helping. It was her idea. So where we found a decrease in NEC rate, a little bit good trend towards less sepsis rates, but no difference in cognitive outcomes, which may be due to the fact that on one hand, we gained a few babies 30 IQ points because they didn't get a NEC and they had a better outcome, but we might have lost 1 or 2 IQ points in the majority of the babies because they didn't grow so very well. Okay, so how to overcome the problem, and now I'm coming to the core of my talk here, is about we added an extra point, individualized fortification, and we measure fat, protein, carbohydrate content, so that the goal is to receive or to produce a standardized intake for preemie babies. So basically to get ISO 2001 standard norm to breast milk, which is not easy. So there are 2 ways to do it. So you can measure now with the milk analyzers the content of breast milk at the bedside. These devices part of the devices were made for the use in dairy industry, and they are using infrared technology. So they're basically measuring absorbance of this moiety called breast milk, and then try to find from different wavelengths, they attribute it to different substances here, and then you can do with appropriate calibration, and if you have enough data points, then you can say, okay, that this here, or the difference between these here corresponds to fat and to protein and to whatever content. However, infrared has been used in chemistry a lot for single substances. So you see that for lactose, the infrared spectrum is very, very fine here with a lot of absorbances here. But if you have lots of products together, then the spectrum looks different. The thing is that between different species, this is sheep, goat, and cow's milk, the spectrum looks a little different in certain areas, and that can confuse the readout. And human milk is different from cow's milk. So the matrix is important, but human milk is different because the protein to casein, the casein to whey ratio is different. We have different fats in there. And the carbohydrates are also different because human milk contains lots of oligosaccharides that cow's milk is nearly free from. And then we do strange things with breast milk. We aliquot it, we freeze it, we pasteurize it. So there's a lot of things that could change the matrix. So there were some initial validations, and I go through this very fast because I had presented that before, which didn't give consistent results. So this is the same device developed, analyzed by 2 different groups, and basically you should find ideally all data points close here to the black line, but they weren't, and they were completely different between the different investigators. So we said we have to do it ourselves. So we developed a few methods and did that, published the methods, and they were validated, and then did the validation. And so here that for the x-axis is always a reference, and the y-axis is the readout, that we have significant errors in there depending on which devices we used and which macronutrients we were measuring. So we tried to fix the problem partly together with the manufacturers, and sometimes a little bit also on our own, developed algorithms. This, by the way, are the 2 devices also are not measuring the same thing, because then we should find it here. So the 2 devices measuring also differently. So we tried to fix the problem, and we're able to do that here by using correction algorithms, also talking to the manufacturers. So at the end, that could be used. And I skipped this here. We have done a little bit more here. about validation studies here and the influence of pasteurization, and we implemented good laboratory practice, and I will show that to you. So basically, we created calibration samples that we and quality control samples that we used for these devices. That was new. I think nobody has done that before, and showed here about over a few hundred days here. So it's about 65 weeks of measurements. That it was stable, but there was a little slight trend in there. But sometimes we had a little bit of misreadings, and it also saved our life one day, because we changed this measurement cuvette here, which has a defined pathway in here, and all of a sudden got a different in the readout, which we would not have seen from the normal variation of daily measurements, because the variation would have covered it, but because we found it with our calibration methods, we found out that there was a little bit of glue of this new device that we used that increased the path length and therefore the readout. So we would have completely measured wrongly this breast milk if we would not have used these calibration and quality control samples. So basically, we implemented good laboratory practice, and I think Myris is doing that as well now. So then, to make that a little bit more robust, we send out, we made a collaboration between different centers. So there were about 18 centers in Europe and in North America, and we send out the same samples to look into the device performance. We looked into long-term stability and quality control, and we also send out a ring trial, which means every unit gets the same sample. They don't know what it is, and they send us the data back. So basically, really good laboratory practice. So this is what we found for here for milk, and here for for fat, and here for protein. And again, ideally, all data points would have been here, but they aren't. So this is protein. You see they're a little bit all over the place. We had different devices, were 3 different devices being used. They were all over the place. Now imagine people do target fortification and measure this way, do target fortification and measure this way. There's a difference of 1 gram of protein in there. 1 gram times 150 milliliters is 1.5 gram. So you produce terrible results in a study, right? So we said, can we also calibrate these devices? We did. Here you see the individual performances of these units here. You see here, this is all over the place, has a lot of analytical, pre-analytical problems. This one is measuring very, very nicely. This one as well. Here there's a time trend in it. So at the end, we could fix the problem. Where they were all over the place here for fat. And after implementing this correction algorithms, you see that these 10 units were working very, very well. So the problem could be fixed by talking to these analyzers, so to say. So we had units that were very low performers, regardless whether we used high or low fat quality control samples or high or low protein quality control samples. They didn't work, and others worked very, very well. And that basically was a handling problem. So with teaching, a lot changed there. These were the data of the ring trials with the expected values, and this is basically over a period of 10 months, 10 samples that we send out. And you still see it has improved. They are close to the expected value, but still some variation. I skip this one. So at the end, we submitted an abstract in 2017, and at the conclusion, I wrote, the observed variations in measurements between centers are clinically significant and would impact the outcomes of clinical trials assessing the adjustment of nutrient intake in human milk-fed babies. This study shows that GLCP must be introduced to bedside milk analysis to avoid confusing results in breast milk research. Okay, we recently had a systematic review of 64 pages looking into human milk analyzers in neonatal intensive care unit that was published in Clinical Perinatology. I think we put everything together that was available at that time. Okay, now I will show you the data of 2 trials. One is our pilot trial here, IFO study. Here, 10 babies recruited. It was a feasibility study, 860 babies, 26 weeks. and we started this fortification at 34 days of life. That is relatively late, but we were very careful because it was a pilot study and a feasibility study. So basically the babies were around 31 weeks of age, then when we did this target fortification, we achieved a weight gain of about 20 grams per kilogram per day. And we were very happy. We said, that's great. And then we made a mistake. We looked into a double-matched control group because I said we need to know what is our normal growth in these babies. It was not a mistake. Managed to find babies, matched pair, 20 against 10. So basically we have the same data here. And you see 19.7. So we were disappointed. We say, so we don't need to do target fortification. It's not worth the work. But then we looked into the feeding volumes that the babies got. So the babies, the matched pairs got 155. These babies got 147 only. So basically, there was an interaction during nights between nurses and fellows. Because, no, we found it out. It's really true. Because the babies grew. No, not at all. Okay, I don't comment on that. I don't know whether we are lucky or unlucky if it doesn't happen. So it happens. So it happened in our unit. So basically, we did an education because nurses were concerned that babies would grow too fast, so they cut back fluid. So then we did something. We plotted here milk intake versus weight gain. And these are the babies on target fortification. And you found a clear relationship between milk intake and growth. Whereas the babies that were not on target fortification, on standard fortification, were all over the place. And these babies didn't grow. So do you recognize the pattern? The pattern is these babies on standard fortification grow well because they are above average protein content of native human milk. These are not, and these don't grow. And we didn't see these babies in target fortification, but only in this standard fortification. So basically, this is about this 1/3 to 40% of the babies that receive breast milk that is not rich enough and is violating our conditions. So we did education on the nurses. We also put a book together here, which now consists of about 50, 60 pages about what to do with target fortification and what not to do. Then wanted to start a randomized control trial. And we'll show you the data in a moment. First, I would like to show you the data of another randomized control trial that comes from Australia, from Karen Simmer's group from Perth, and Gemma McLeod's, I think it was her PhD thesis. And she did this study in 2009, but it was published in 2016. So 7 years in between. And she did 20 babies with individualized and 20 babies with regular fortification. And they had the same gestational age, birth weight was the same, full enteral feeds achieved at the same day, all fine. Weight at start of fortification was also more or less the same, no difference. And then discharge weight, no difference. So disappointing result. And she wrote, so target fortification may be not helpful. But she admitted that she used a device that was not calibrated. And when we look into the data, what she did, what she gives also in the paper, then you see the following thing here. This individualized, this is the regular fortification. Fluid intake for regular is a little bit lower compared to the individualized. The protein to energy ratio is 2.6 versus 2.7. So there is no difference. So if she doesn't aim for a difference and she has the same intake, then she will receive at the end the same growth. And we know 2.7 is not enough. We need far above 3, up to 3.6 to achieve good growth. So she basically set her expectations too low for what the babies should get. And you see it here. Also the energy intake, 524 versus 538. That is maybe not enough, and the protein intake was also the same. So in our study, we tried to evaluate the effect of individualized target fortification of breast milk for fat, carbohydrates, and protein on weight gain of preterm infants compared to routine fortification in a randomized controlled double-blinded study. That study was funded by the Canadian Institute of Health Research, CIHR. So it was a double-blinded, single-center, randomized controlled trial, 3 weeks of intervention period minimum, randomized using sealed envelopes, primary outcome weight at 36 weeks, and we had lots of secondary outcomes. These are 4 of those. So, some German, Kontrollgruppe, which means control group. Standard fortification also, right? So you get a free lesson here. Is just milk measurements, and the intervention is milk measurement plus the target fortification. And the aim is, so Ziel, sorry for that. Ziel is Aspergen recommendations for protein carbohydrates calculated for an average intake of 150 milliliters per kilogram per day of mother's milk, Muttermilch. Milk analysis and TFO adjustment 3 times per week, Monday, Tuesdays, and Fridays. That's not true. Monday, Wednesdays, and Fridays. That's wrong. Sorry. And we measured also on all other days the intake. We got all other breast milk samples and measured the content. So we really knew what the babies got at the end. So this is the sheet that we used. This is the content of the sample of breast milk. This is what we add by adding the standard fortifier. This is what we add up with. This is what we would like to see, and this is what we add. So we add polyglucose, beneprotein, and microlipid in this baby. We decided to measure only 3 times per day and not every day. If we would have measured every day, then if we look here for protein, then you reduce the variability. Then I think we are running out of juice here. Then you reduce the variability here. Yeah, that's it. Yeah, not me, but that. Yeah. So then we are reducing the variability here of protein. If we measure only during weekdays, the variability of certain babies goes up depending on the variability of the mother's milk. The average intake is still the same. Here we do it on 3 days, Monday, Wednesday, and Friday. You see the variability goes more and more up. Here it's only once per week. And there are already certain babies that now get much less than they should get. This is native breast milk. This is standard fortified breast milk. And this is with these different fortifiers, with these different schedules. And that's the same for energy, and here for carbohydrates, and here for fat. So we decided we go for 3 times a week to have an optimum. So this is a Consort diagram. We had at that time 427 babies that were eligible. We randomized 179, and the study started in 157, and we finished in 103 babies, the study, so 52 and 51. Here, the completed, randomized, and started. There was no difference for all these different groups at the end for maternal characteristics. There was no difference between infants excluded in the control group and the TFO group. And these are now the data. So these are the babies where we included 970s to 960. These are the demographics. And here, the maternal characteristics for control versus TFO, there's no difference between randomized and completed as well, and not between groups. And now I show you the difference of intake that the babies got. So this is the control. This is routine fortification, so no intervention. This is with intervention, but before intervention with routine. So you see there's no difference in the protein intake if the babies would not have received the target fortification. With target fortification, we end up here in that group. So the baby gets significantly more protein. This is for fat. You see, again, both routine, no difference. So that's good. And with the intervention, we add a little bit of fat only. That is due to the fact that fortifiers in North America add a lot of calories by adding fat and not a lot by adding carbohydrates. This is for carbohydrates. You see here, again, no difference. And this, again, are the donor milk babies. And this is what we add in the target fortification. We add a lot because the North American-based fortifiers don't contain a lot of carbohydrates. It's different with the European ones, they are the other way around. Caloric intake is increased from 115 to about 133. These are the growth trajectories of all babies here in these 103 babies. These are the weights at 36 weeks. In the control group, 2,280. In the intervention, 2,510. That is highly significant. Growth velocity is higher, and the nutritive efficiency, which I calculated and defined it as growth velocity per TFI, that was important to do after the experience with TFI, was significantly higher here, and the TFI was the same in both groups. This is a graph. So again, this is the intervention, are the blue ones, so the TFO. These are the controls. So you see between intervention high protein and intervention low protein, there's no difference. Makes sense, that is logical, because these have a high protein content already in native breast milk. So we don't do a lot of intervention here. And this fixes the problem and comes up to where we should be. The control with high protein content is also no difference because there's already enough protein in there. So the major effect you see in those infants where that receive breast milk with a low protein content. That was to be expected. Yeah? So that in this group we would not see an effect, but in the lower group we would see an effect. Maybe I forgot to say that this is stratified, so it's not only about intervention versus control, but we divided them in protein above the mean and below the mean. So if you look at that in numbers, control versus intervention, 2,400, 2,480. No effect. No wonder, because it's a high protein content in native breast milk already. So there is not a lot of intervention happening in the intervention. But low protein, 2,170 versus 2,540. So about half of the babies would benefit from the TFO. The other half would not. We would measure, but we would not change practice because the content or the energy is already high enough. So that makes a big difference in this group. We have some other data here about perinatal characteristics and NICU outcomes. And interestingly, there is only one thing significant, that is feeding intolerance. And the feeding intolerance is lower the rate in the target fortification group that receives the intervention, though they get more, interestingly. But they get consistently more. And maybe that is better tolerated, I don't know. But this is a big difference, 15 versus 27. All other measures here, like BPD, PDA, so the all three-letter diseases, are in favor of TFO, but do not reach statistical significance, which is sad, but maybe we need a bigger number, and that needs to be repeated. So if we figure a little bit on feeding intolerance, then you see here control, intervention, look into the complete ones, and then you see here no feeding intolerance, 36 babies versus 44, one episode, 11 versus 7, and more than one episode, 3 versus 1. And day of life and PMO, was all the same here. So apparently they tolerate this TFO relatively well. In terms of blood chemistry, there's no difference in glucose. This is all babies, control versus TFO. This is a high protein and low protein group, so subgroup analysis. But you see a difference in BUN. So the BUN rises a little bit from 2.5 to 4.5, and that is consistently through the high and through the low protein group. And the triglyceride levels go down a little bit from 0.9 to 0.7, and that is also consistent. But it doesn't reach statistical significance. So it looks, this difference here is not clinically significant, and this here is not significantly either clinically, but it shows maybe towards a better metabolism because babies get a more reproducible intake. We also measured body composition. We got that analysis done, not in all babies, but in a subgroup of babies, and found that the percent fat mass increased a little bit. So the fat-free mass increased here from that's a lean mass here. And it increased a lot here in the low protein group from 2,360 to 2,710. But fat mass increased as well. And that is something where I'm not too happy with. I would have rather seen that we stay maybe around 20% and not about 22%. But I think we have an explanation for that. And that is because of the composition of the fortifiers. I told you here we have Enfacare and Similac. And this is the composition: fat, protein, lactose, and energy. And you see here, and these are the European ones, Nestle and Milupa. You see that the protein content of these fortifiers is all the same. You see that the fat content of the North American ones are relatively high compared to the European ones, and that the carbohydrate content here is higher, and basically here there's not a lot of carbohydrates in there. So that means that if you go back to the data from Sutta Keshyap, where you feed babies the same calories but give them more fat, then they accumulate more fat and don't grow so well. So if we would at least have a better composition here of a fortifier, maybe a mixture between both, and Nestle and Milupa have changed their composition now by introducing more fat and taking some of the carbohydrates out, we are coming close to the better composition, because we over-fortify a few babies with fat because the natural fat content is already so high. So we can't take the fat out, right? And the price to pay is maybe that we have a little bit higher fat mass. So there is a relationship to it. Okay, so this is the second last slide before the conclusions, and then you are dismissed, so to say. What we have done here at the end is a big biological experiment, because we use the natural variation of breast milk, and we know exactly what the babies got because we have really measured everything. Because we used the natural variation and topped it up, we have a range from 2.8 up to 4.6 gram per kilogram per day of protein intake. And here you see the different groups. This here is the IFO high protein group, so high protein with intervention. This is the IFO low protein group, so low protein with intervention. There's no difference for the protein intake. And you see here the donor milk samples are also in that range. For the routine, so the non-intervention period, you see these here with high protein are here. And there are the ones with donor milk. And here are the ones with low protein content, without intervention. And they grow worse. And you see where all the donor milk samples are. The good thing is the problem with donor milk can be fixed, as you see, because they all go here. So if we do donor milk with appropriate fortification, we might see a benefit from necrotizing enterocolitis, from sepsis, and also for a better neurological outcome. Okay, analysis to follow. I have shown you already a few ones. Neurodevelopmental I can't show you yet because the last baby is being assessed in April. Okay, so I come to my summary. Target fortification is feasible and reduces the risk of postnatal growth restriction in babies from mothers with low protein content. Important, target fortification is not providing super fortification. It just identifies those babies with mothers that produce breast milk with insufficient macronutrient composition. To measure solely protein content might not be sufficient. Fat content is highly variable, as it is the lactose content. Donor milk can be reliably measured. Pasteurization does not distort the analysis. The optimum components for target fortification need to be developed. The fat-based concept of fortifiers available in North America to provide the extra calories needed should be reviewed. And the concept should be proven in a blinded, multi-center, randomized controlled trial, including body composition measurements and neurodevelopmental outcome. Then I learned in a recent talk that the audience are likely to remember only 3 things from my presentation or speech. So I break it down. Breast milk is best from a bioavailability, digestibility, holistic, whatever it does to mom and kid perspective, but may provide a highly unstandardized diet for preterm infants that are not self-regulated and can put growth-associated outcomes at risk. Target fortification is feasible and seems to have an impact on growth and other outcomes. And the third is more research is needed. And acknowledgements of a few of my group, Canada Wonderland, and thank you very much for your attention. Now I need a wine.
He needs wine, man. Okay, do we have any questions? Yep.
It seems like there's been so much work on the neonatal end, and this target fortification is clearly fascinating and shown amazing results. I'm wondering, has anybody looked at what we're talking to our moms about? Like, because we don't do a whole lot of coaching unless there's like digestive problems with baby. Hey, what are you eating in your diet? That kind of thing. I'm just wondering if anybody's looked at what's going into mom versus what's coming out, and could we do a little more on that end?
That's an excellent question, because if we would find a way to, let's say, modify the diet of the mom, and breast milk would have a different composition, and we could fix that problem after milk analysis, so to say, then we would not need all this business. Unfortunately, all the data so far show that you have not a lot of influence on macronutrient composition. So now eating a lot of steaks or protein intake does not increase the protein intake, unfortunately. Body composition does it. So a mom that has a little bit more robust body composition produces a little bit different fat amount, but not everybody wants to have that at the end, because they all want to lose after. Right? There is some influence of dietary intake, so I'm not misunderstood. So if you eat, so the fatty acids that you eat, that goes into breast milk. So if you eat more omega-6, omega-3 or whatever, that profile, you see it immediately. For a few vitamins, like vitamin A, D, it works as well. But unfortunately not for the amount of lactose and of the macronutrients.
So, if anybody's feeling not very robust this evening, needs more food, Dr. Fernandez in the back. In German, please.
No, yeah, a long time ago. So, that whole thing about breast milk is best. When I have a child from the NICU in the outpatient clinic, or just a 1-year-old who's still breastfeeding or failing to thrive, we still try to push breast milk is best. But now I really worry about, trying to get the kid off breast milk and putting them on something that I know what the protein delivery is and calorie content is. So has any studies, or is anyone trying to do this as an outpatient basis on the kidney?
Yeah, I think the problem is not so much present in outpatient or when the babies are beyond term, because growth rates slow down so much. It is really a problem from these 24 weeks up to 40, where you have also a lot of brain growth, as you see, and that's where it is. Once you are closer to term, I think the composition of breast milk doesn't matter so much. Though in a single baby, it might be that it doesn't get enough because there is no fat in breast milk. There are some mothers that produce extremely poor breast milk in terms of fat content, and that can be in single cases. But I have no, other than measuring and looking into growth patterns, there is no magic bullet or formula where I could say, now you should switch over.
Well, okay, so that was my question too, is that when a baby is born early, the mom isn't ready to produce milk because the baby's early. So how good is that milk? Like, and because she hasn't gained weight because And also, when we fortify that milk, a lot of times the babies will spit up. They don't like the fortification. The majority of the time, it takes a good while for them to get used to it.
Yeah, that's.
So they are going to lose weight.
This paper here is from Tanis Fenton, right? So what she did here is a meta-analysis or a review of all published data about true protein content. And this is preterm milk and this is term milk. And you see that preterm milk, yeah, the variability is higher, but it's basically with the average here within comparable to term milk.
Okay.
So even sometimes a little bit higher in protein content. So it's not a bad milk, preterm milk.
Okay, it just takes a little longer.
Yeah, yeah. Okay. And the amount of fortification, yeah, that's, I mean, very frequently people ask, so what do you do with this osmolality if you add all this stuff, right? So what about neck and all that? And I must say we have measured osmolality. I didn't show the data. And we rarely went above 460 or 480 milliosmoles. Sometimes we saw that we were higher, but then there was a mistake being made by weighing in. Or we were below, then we really saw there are components missing. We published a paper on that because you can really predict the final osmolality and you can say what is missing then at the end. But apparently this whole thing about osmolality and neck and tolerance is on very, very weak grounds and comes from two pediatric surgeon papers from the 70s where they used a formula that had 300 milliosmol versus a semi-elementary with 700 milliosmoles and gave it to preterm babies. And all of these 6 or 7 preterm babies got a necrotizing enterocolitis. And yeah, it was a little bit heroic to do that. And then they said, okay, maybe the truth is somewhere in the middle. Let's put a cutoff on 450 milliosmol. And that is very, very weak data. And that is basically, that has been published in the early 70s. And from that, there was only copy-paste, nothing new data, nothing on it.
It's hard to go past that, though, if you know that's your safe place.
Okay, but
yeah, but the data, it has just been, it's one study.
But the irony, here's the irony. I will tell you that we sometimes indiscriminately add to the feedings sodium chloride, potassium chloride,
Iron, coffee,
phosphorus, calcium, vitamins, and so on. And the osmolarity, when you add that, is over 600 frequently.
You only get 2 millifilms for every 1 millifilm of sodium.
Yeah.
So it's a small amount.
So Paula Radmacher published a good paper.
That you're getting. For each 1 millifilm per kilo, you give 2 millifilms per kilo.
50
Sodium
milligrams.
and potassium.
Yeah. So let me present to you with the following, because I think that we have tried to improve, and I think we're still far from improving what we need to do nutritionally. We absolutely control, like when we tell Elizabeth we're going to start the kid on this antibiotic, we know the milligrams per kilo. When we write TPN, which is the overwhelming majority of the babies, we painstakingly go through each component and decide the baby's going to get this many grams per kilo, this many milligrams, milliequivalent. We do for all of that. When you decide to feed a baby a formula, there's a fixed component. You know exactly every can or every bottle, every something has the same. But then when it comes to feeding and feeding breast milk, we have absolutely no idea. The variability is so dramatically different between a mom at any given time, between the mom in the morning and the evening, and of course between moms. And then there's the paradigm that a big proportion of our babies gets donor milk that has a dramatically lower content of some key components. So I think that last I checked, there weren't any new methodologies to treat these babies. There weren't any new medications to make us better. There weren't any new pieces of equipment that are going to be saving more preemies. just about the only way we have to improve their outcome is to improve their nutrition, something we do every day. And I, for one, think that if we really get serious, we have to be feeding with the same painstaking ability to measure what we're given, like we do with everything else we do to those babies, except the one that is the one intervention with the highest likelihood of improving their outcome. I've never been able to understand why we look at it so casually, and we do.
I think it's a new area at the end. I mean, we know a lot about ventilation and what we should do and what we should not do, and about sepsis rates, about outcome. With nutrition, we know a lot, but it's relatively fresh and new, and it's also, I would say, it's a different kind of philosophy. The ventilator adaptation, the guys, they do this one, right? And the nutrition guys look a little bit more about fluxes of molecules and metabolism, so it's a different way of thinking. And there was long time there was no way to look into the efficiency or the effect of nutritional intervention, because if your sepsis rates like crazy, if you have BPD rates like crazy, then you don't need to do that, because with each sepsis rate you go back to square one. There's too much noise in the system. And if, as you have sepsis rates under control and your BPD rates come down and there's no IVH, or that is coming down, then nutrition comes into place at the end, I think.
Do you ever look at energy expenditure in terms of asking your babies to PO feed a little earlier, PO feed too much too soon, wean out or isolate too, like asking too much of them while trying to, stop moving. Like, no, I'm just kidding about stop moving. Moving's good. But I always think there's an energy output that we don't necessarily are not cognizant of 24/7. But we're always trying to get them to gain weight and stay on that growth curve. But we're not cognizant of what are we asking them to do on a daily basis. Are we asking them to PO feed too much? Like, cut them a break, man. They weren't even supposed to be out for another 4 weeks or 6 weeks, you know? I just wondered if you had ever, or anybody ever looked at that. I ask this question literally every nutrition lecture I want.
Naja, they're not supposed to be out. That's true, and mom is taking care a lot of a lot of functions, right? But now the baby's out and has to fight a little bit, take care of itself. Has to do with different thermocontrol and whatnot, breathing, whatever, right? So it would be great. So I think we have two variables that makes the babies grow apart from genetics. That is, on one end, what we feed into the baby, and the other one is what are the needs of the baby, right? And there are babies that might be more active, others don't, others have a little bit more problems. So it would be great if you could measure energy expenditure, or at least movements. And we are starting to do that. I'm just setting up a system where I look into the spontaneous movements and will correlate it with energy expenditure of the baby, measured with different methods. And then see, when we put that into the equation, maybe this baby needs a little less because it's a more acquired candidate, and others are a little bit more moving more at the end. So that is the second thing to improve at the end, growth and body composition. And maybe we can give the babies a little bit less fat or whatever. I don't know, whatever. If we know what the energy expenditure of these babies is. On the other hand, energy expenditure also has to do with how the baby grows. Babies that grow better have a higher energy expenditure, because to build in the protein is an energy-consuming process as well. And there are nice data from Karl Schulze, also from New York, that shows that babies that grow better have a little higher heart rate, because their metabolic rate is higher because they grow better, because they synthesize more protein. So there's lots of things not understood yet, but at least let's get rid of this variation step by step. Now we can get at least rid of these. What really was an eye opener for me was these XY plots of the different components. And goodness, what are we doing there? In some way. And then we just give more.
Can I ask this to just, do you know how often the work at, like how often are they doing what we call like care times or touch times? When we go in there, we take a blood pressure, we assess the baby, change their diaper, everything, because that's causing them to use more energy. You know, if they're upset, they're crying, they don't like us changing their diaper, they don't want to be touched, they're not supposed to be touched, they're still supposed to be cooking. So, do you know how often, just as a thought, like, how often do your nurses go in and do their care times?
So we do that a little bit to the needs of the baby. When the babies are more stable, we do it much less. So sometimes every 6 hours only, or sometimes only once per shift.
Is that right?
Yeah.
Only
6
hours?
Yeah.
Once every
Yeah, we don't want this point to get lost in translation here. So the question was, we're very dogmatically going in and doing things to the baby and potentially altering a little bit their metabolism, increasing energy expenditure. What Dr. Fuchs is saying is that as the babies become more stable, they are intervening less, not on a fixed Q3 or whatever hour schedule, but a lot less, and that may be something that we may need to ponder as well.
They might not change diapers then every 3 hours.
Especially if they're dry. So the temperature is really important. There's been really good measurements that say that from inside to outside the isolate is about a 6 to 10% increase in energy expenditure, but it's very transient. Okay, Brenda, and then Elizabeth.
I'm particularly interested in children with IUGR and SGA.
Can you try to keep it a little down so we can hear the question?
All of your research, all of the things that you're looking at here, was there anything that stood out to you with that particular population group of the SGA and IUGR babies, particularly interested in increased caloric needs or increased different dynamic of the formula that they need?
Yeah. So in that study, we have not included the severely growth restricted below third percentile. So I can't say anything about that because all this catch-up growth is a little bit a question, right? So if you would need to assess what is the genetic potential of the baby. Is it small for gestation or light for gestation? That's the first difference, right? Small or light. Then is it because it's constitutional? And maybe it continues to grow there where it is. And so it's just a statistical effect because parents have the same genetics but doing well. Or is it a baby that was growing below the genetic potential? And then where is the true potential? So where should the baby go then? There's some data from Olivier Claris' group from Lyon, the previous chiefs there. Audiproc is it called? And they tried to develop a formula according to maternal height and so on to find, yeah, it's a pretty neat thing to see where is the approximate percentile of this baby, and then you get an idea. I mean, it helps you a little bit to see the genetic potential would be maybe in the 50th percentile, but the baby's on the 10th or on the 8th, then you know, yes, okay, that's really a big difference. Right, so it's below the genetic potential. And then we still don't know what would be the catch-up. Is that already irreversible from this? Because it's a long-lasting effect. So is there some epigenetics already affecting on the baby and it can't grow? And we make it only fat. So we need to measure body composition on these babies as well. It's very important.
Yeah, the growth-restricted baby is probably a whole different
matter. And you might need to go with head circumference much more as well. Right?
Yeah, Elisa?
I know this was a kind of a strange question, but we just changed how we were giving electrolytes so that we gave them separate from the formula. Because some places add electrolytes to the formula. So you've got 100 mils of formula, and once you add electrolytes, it might add up to 120. So baby eats a certain amount, and so now we've diluted out those calories. And so we've changed so that we give electrolytes separately. And some people add like different things to formula. They're like, oh, we want to add the MD out of formula, these types of things. Has anybody looked at different centers and how they decide what goes into formula, what doesn't go into formula, what should be given as a separate med, and whether that affects growth. Because once you add too many things to formula, my 100 mils of formula that I just measured that has an X amount of calories is now up to 120 mils of formula. And so what I thought the patient was getting is not what they're getting. So has anybody looked at all these things that people think they should add to formula or should add outside of the fortifier? Is it the right thing to do, or should people give everything separate so that we know that the calories and the protein the patient gets is what they're getting?
I'm not aware of data that looked into different ways giving all these add-ons that we give, be it, I don't know what, calcium, phosphorus, iron, vitamins, whatever, caffeine, electrolytes, bicarbonate, or whatever we give.
Some people add it to 100 mils of formula.
Yeah.
And then the 100 mils of formula is now not, it's 110 mils of formula.
Yeah, but so I don't know about any data about that. As said, Paula Radmacher looked into what is the final osmolality. If you put that in, there are pretty robust data on that. I mean, if you prepare 100 milliliters and you know what is in there, right, either formula or whatever, and then you put 10 milliliters on top with electrolytes, and you feed the 110, then it doesn't matter. It only becomes a problem if you give up. Yeah, that's a problem. So then you down dilute by 10%, and that is something that's definitely not good. Then you need to feed the 110.
I don't think that's what standardly done. I think people the nurse has an order that says 35 mils Q3.
I see the point.
And she gets 35 mils Q3, and it doesn't matter if she has an order that says.
So when you do round. So when you do the rounds, then you say, okay, the baby gets 8 times 40 or whatever, or 8 times 20, doesn't matter, right? Or wherever we are, and then so you prepare your 160 milliliters at the end, 8 times 20 or whatever. So you prepare your batch, right? And then you put the electrolytes in, or do you put them in for every single? Did you put them in for any single feeding that you give?
We've separated that.
I think we found that part of the problem was that people were adding it to formula, and some of the nurses added it. It was 100 mils of formula. Some of the nurses QS to 100, and some of the nurses did 100 and then added it in. So we had no idea.
Yeah, okay. So I mean, if you do that you have 100 and you add on 10 or whatever, and you feed only 100, then you down dilute, and that is terrible. Yeah.
Yeah. That happens all over the U.S.
So what? But
or probably in Europe as well.
And you are scared to feed the 110 because of volume, because of TF. Yeah, that's.
They spend so much time fortifying the formula, but then nobody looks at what we're adding to formula or adding. And I think all that stuff should be given.
It's very interesting about these TFI restrictions that I experience in North America, because we are usually 150, 160. And if I would say the baby gets 180, I think then I'm close to getting problems with the attorney. Yeah, but look into the data that have been published now. I mean, our babies have considerably better pulmonary outcomes now, and they easily, even the tiny ones, tolerate up to 200. There are data from look at Anne Janvier from Montreal. She recently published a paper. Recently is good, 3 or 4 years ago. She published a paper where she showed that she can improve growth with improved nutrition, and she feeds up to 180 or 190. So that's a North American paper. Look into that one at least. And we have published one where we went up to 200, and that works.
In fact, the evidence to support what we do with fluid restriction for kids with chronic lung disease has absolutely no bearing, no scientific. I think to add to that, although we don't want to deviate from the theme, is that what we don't do is question what we do enough. We just add stuff. And you know, we need to reflect how much do the kids really need it. We don't take into account that for every order we give, the potential for doing harm or diluting the milk, like we said, or increasing osmolarity, or giving too much of a thing, is in our thinking. We just very often, very dogmatically just add something and never question. I think we need to control, police ourselves a little more as to whether we really Okay,